It's really nice to talk to people who want to learn about robotics. But I suppose many of you have already done courses in robotics? Or what is the level that, because I am going to get into fundamentals. I can see Vishnu already there, so he is teaching robotics in Ahmedabad. But I am sure there are students also. So I am really going into the basics. Some of it may be a little known to you, but if you want me to go fast, just let me know. It's really nice that Sri Mukherjee talked to you just now, and he must have given you a perspective on how to develop something which has to really work on the field, and that is not a small thing at all. I was also associated briefly with that work, the initial stages, and I could really see the amount of effort and struggle that happens in a project like that. And the kind of questions which came up about intelligence and obstacle avoidance, many of these things come much later, after you are able to develop a good platform. And what you saw, I suppose, was development of a very good rugged platform for very tough, very difficult kind of environment. It's good that you had an introduction there. So I will start off with fundamentals. I'll be talking to you twice. The first talk is a sort of overview again of robotics, particularly mechanisms. So it's not just an overview. I get a little bit into mechanisms, still at a fairly broad level. And in the second talk, we go a little more into detail into mechanics and mechanisms, particularly the kinematics. Kinematics is my background, so it's quite natural for me to do this. So we'll, to start with, see some robots in action. You must have already seen some. I'll take you through a few more. So before that, that thing that you see on the left looks like a knight in armor is the first concept of robot, or the term robot arose in a play which was made in 1921, and that costume worn by and the so-called robot is what you see there. And when I was young, in school and college, there was this Flash Gordon comics, where this Flash Gordon was a traveler in space, and he had robot enemies and robot friends. And the concept of robot then was very advanced. In the sense, a robot was capable of traveling in space, being on planets, act by itself autonomously, fight people, fight men, fight each other. So it is as far as we can take robotics. But reality, of course, was far away from that. So just one question, are there robots like that now? Robots, if not fight, at least move around like people and react to stimulus and things like that? So, yeah, there is a robot called Asimo made by Honda in Japan. which we'll see that looks very much like a human being. But the key question is not moving like a human being, which also is not easy, but thinking and having intelligence. So have we reached that? That is not easy. Of course, we haven't reached that, obviously, but that is what we are trying to do. But, so let us look at actual robots. So what you see on the left there is what is called a serial chain robot. This is called a motorman robot. It's a very simple configuration which we will see a little later. We'll see it in action first. I haven't embedded this, so I'll have to play it on one side. So this is a typical operation in a factory floor by a robot. So it is picking up something of a part presenter, and it is placing it on a bin or a pallet. And look at the robot. The mechanism of the robot is what is quite interesting. And it is moving fairly fast. The large motions it has to do is being done fairly fast. So I just wanted to show you the motion. So this particular configuration is called SCARA, which we will see later. So now the one on the right of that is made by a company called ADAPT. It's called the Quattro, and this also does pick and place. So let us see it doing that pick and place. And the claim is that this was the fastest robot at that particular time when they made the video, which is a few years back. So the answer to the question, can robot do this kind of pick and place as fast as humans can? The answer is very obvious, right? We can do it much, much faster. So we cannot match anywhere near the kind of speed that we saw there. And what is interesting about this robot and the previous one, if you compare, the mechanism used are very, very different. Okay? What we are going to concentrate on this in this particular talk are the various mechanisms which are used in robotics. And you see a very different mechanism here. Okay? And it's very fast. Even this particular robot, the Motorman by itself may not be all that fast, but this company ADAPT, the second one, the company ADAPT was making robots which were very fast right from the beginning. They had robots of the same configuration as the Motorman, which is very, very fast. So you can see it in YouTube. The one down here is very, very fascinating. This is really not a robot in that sense. It is a device for helping surgeons do surgery remotely, and much better than what they can do when they do surgery directly. Okay? So you see the surgeon sitting on that console. He is the surgeon. So the surgeon is sitting there on the console. The robot is here. The patient is lying here. There is an assistant here which is helping out with a few things. The operation is done by the surgeon by moving a few things which we will see in the video, and these arms get inserted into the person and it does the operation. Okay, so let us see the video there. This is what the mechanism looks like. Something like 4 arms. This is one of the most important parts, the end effector of the gripper. And the surgeon is manipulating or moving this. So this is called a master-slave configuration, and this is the master at the fingertips of the surgeon. And this, what is being done here is not at all easy to do. It's a very, something which requires a lot of skill. Okay, so there's this also is called a robot, but this is not exactly a robot. It is entirely controlled by the surgeon. But there are some very interesting things. One is that this particular surgery doesn't require that kind of fine operation. But if you want to operate on the eye, okay, and if you want to operate on blood vessels, which are very fine, the problem is that the typical tumor that we have on our hand is larger than the size of the blood vessel. So how do we operate on something like that? So what Da Vinci does is that it takes the tumor away. It filters out the noise, takes tumor as a noise, and filters it out. And the end effector, the knife and all those things moving there are much more steady than the human hand, although the human hand is controlling it. Okay, so this is one very important thing. The other important thing is that when we do something with our hands, manipulate something, a lot of our ability for doing this comes from the feedback we get through the force feedback that we get. Okay? The sense of touch, the forces that we feel in our hand. And if we don't have that, our ability to manipulate will be much lower. Da Vinci has the ability to give feedback to the surgeon, the force feedback to the surgeon, but it turns out that many of the surgeons feel it is not required, because the visual perception they have is so good that the force, they feel they don't need the force feedback. Many of them use it without force feedback, but that is available with Da Vinci. So this is a master-slave configuration. All these are what we call manipulators. Okay? Then of course there is a class of mobile robots which Mr. Mukherjee was talking about. So we will see a few in action. The first one you see there is a vacuum cleaner, and the one on the right called the big dog, now it is called something else, was developed by Boston Dynamics for the US Army. What you see there, developed by University of Essex, is a robot fish, and it was mentioned that about Asimov, a human-like robot. So we'll just see all these briefly. So you will start seeing a bit of intelligence as these robots operate. Yeah, there is basically a lot of advertisements. So yeah, so look at this vacuum cleaner moving. So this is autonomous. Okay, it's just let free onto the floor. It is moving on a carpet. So this is an advertisement video, so you see all this. Now see what it's doing. It has gone under that sofa, and normally we find it difficult to clean below these objects, but this is able to go around and go into very intricate regions and clean. Okay? How does it do that? Okay? This is the interesting question, which hopefully somebody will talk about when they talk about control. But okay, what gives it ability to be autonomous and does it do the work it is supposed to do in a room totally autonomously? It requires sensors, it requires information processing, it requires ability to act. All these things are required. In the context of this talk, all that the important question is, how does it move? What kind of wheels does it have? Okay, that is more important. So we'll come to that. Now let me show this amazing rover, the walking robot that I showed. So I will again show it. The one on the right with 4 legs. Okay. Now see what's happening. So that kick is good enough to really fell a person, but this robot has adjusted, okay, and is able to be still stable in spite of that kick. So this is, it works in very different kinds of environments and all that. Now this robot is quite sinister. It is being developed for the US Army. Okay, so who knows? Very soon this, this is long back. Now these have been developed to a much better level, and very soon human beings may be replaced by these kind of things, which may even carry guns and fight. So, and not just remotely controlled like that, but autonomous. So. Here you have a very fascinating robot, that fish-like thing that you see there. The question is, can it move like a fish? So this was developed in University of Sussex. So it's out of water, now it has gone into water. So see how it moves. So can you really distinguish it from a fish by the motion? It is so gentle, graceful, but for the fancy covering, it would have been just like a fish. So again, the question here, really relevant for us, is what is the mechanism? Okay, so we are going to talk about mechanism. I may not get to this, but how do you really build something to give it this kind of a motion? So that is the fish, and finally. Asimov. So the question, have we built robots which can really be like human beings? So at least partly we have, or Honda has. So let me show that video. Yeah, this is the robot coming like a attendant. So let's see what it does. Is it being able to walk because of the support coming from the wheeler there, or can it walk by itself? Yeah, it can. It can even run actually. If you look at the YouTube video put out by Honda, you will see this running. So it seems to be looking at this. I really don't know whether it is looking at it, recognizing, deciding what to do, and do that. The demo of Asimov I had seen was fully programmed. Yeah, it's unscrewing the top cover. Is it easier to unscrew or screw it in? Which is easier? Unscrewing is much easier. To screw it back on is really tough. But even in unscrewing, you have to have a helical motion of the So that's it, that is Asimo. It has been under development for a very long time, and of course in some of these things what we are trying to do is mimic nature, and that is actually one of the biggest fountainhead of creativity in engineering. Observing nature and trying to mimic that and develop systems which are, if not as capable, but follows the principles we find in nature. And in robotics also, that is what we do a lot. We try to develop systems which have the kind of principles based on which nature works. So let us now start looking at robots a little more. So what you have is the mechanism of the robot here. Okay, this is what we will see in detail. But mainly it is a series of links which move with respect to each other, connected by joints. In order to drive the joints, you need actuators. So there are actuators there, motors and things like that. And typically, you need a transmission between the actuator and the joint. So there are transmission elements. And intelligence comes from the fact that it has sensors to understand its own state as well as with respect to environment. The state, and then of course processing of information through controllers like this. So this is typically what a robot consists of, a manipulator consists of. Now what we are going to look at are mechanisms. So mechanisms is basically the skeleton that you see here, and of course transmission elements are also typically mechanisms. This is a gearbox, that is a mechanism. But we are going to look at mainly the skeleton of the robot like this. So basically what the mechanism does is that it enables certain types of motions. Okay. So here, how many are from electrical engineering? Can you raise your hands? So remaining are from mechanical. So much of what I am going to tell you or discuss are things mostly known to you. So, but I wouldn't spend too much time on that. Whatever is important for the electrical engineering students to understand, I will cover. So, mechanism definition is somewhat like this: a set of rigid or resisting bodies which are interconnected by joints. Okay. And through these interconnections, they have relative motion between each other. And typically, one of the bodies is fixed. That is when there can be free-flying mechanisms also, but typically we consider one body to be fixed. So an example is the slider crank, which this is a mechanism which engine, a typical IC engine is made of. This is the piston which reciprocates, and this is the crank which rotates. And there is this connection between the crank and the crankshaft and the crank. Sorry, the connecting rod between the crank and the piston. Now, what is more important than these links, which are called crank, connecting rod, cylinder, and all that, are the joints by which they are connected. It is precisely the joints which enable or disable certain types of motions. So, the joints here are typically the door hinge kind of a joint, It's called a revolute joint. And this particular joint, which you can imagine to be a sliding joint or a prismatic joint. Okay? In this case, it can as well be a cylindrical joint and it will still work. But typically that is a prismatic joint. If you look at joints, okay, conceptually, these sort of give the idea of joints. For example, there is the frame on which this can purely rotate, and that is a revolute joint. And there is this frame on which this can purely translate up and down, because this keyway is here, and this is what is called a prismatic joint. A combination of this and this, which are interconnected in the sense one is dependent on the other, is this helical joint, or the screw thread is a typical example of that. So these are all 1 degree of freedom joint. Degree of freedom means, so I'll come to degree of freedom a little later. I'll define it later. Now these joints are a little different. The only thing different between this and these two is that you have really allowed both motions of rotation and translation here, whereas here they are constrained. Here this particular boss constrains translation and the keyway constrains rotation. Both are possible here. This is called a cylindrical joint with 2 degrees of freedom. And this is a ball and socket joint or a spherical joint, which is actually 3 degrees of freedom. This is like your shoulder. And this kind of a joint we don't typically use. It's called a planar joint. It's more only a concept than an actual joint. So these are more important than the bodies, or the rigid bodies, which they are used to connect. And the type of motion which is enabled is because of the nature of the joints. Now let us come back to our manipulator. There are different types of manipulators, and we are going to see mainly 2 types. One is called a serial chain and the other is called a parallel chain manipulator. Now the manipulator that you see here is a serial chain. A serial chain means, let me see if I define that. No. So a serial chain means that there is a frame, and the frame is connected to just one link through a joint, and this has to be a 1 degree of freedom joint because of a particular reason, and the second link is connected to the next, and so on, and so you have a serial chain. Okay, so all of you have an example of serial chains. Several examples actually. Our arm is a serial chain. Okay, that all of you are able to recognize. So let us look at our arm. What sort of a joint is there between the body and the upper arm? It's a spherical. It's a ball and socket joint. It's a spherical joint. Now, which is the next joint? So this is the frame, and then your upper arm. That's the next link. Now that is connected to the lower arm. And what is the connection? What is the type of joint? There's a revolute joint. Okay. And then what do you have next? Now there are several things here. It's very complex. So if you make it simple and close it, it is like a rigid body. So the fingers are not there. Okay. So assume that this is a rigid body. You have the fist and you have the lower arm. What is the joint between the lower arm and the fist? Spherical.
Spherical to some extent.
Spherical to some extent. Yeah, that's correct actually. Yeah, your notes. That are more technical terms, but very simply, what is the kind of joint? So you see actually 2 types of joints there. So that almost is very correct. If you hold the elbow and try to see what kind of motions this can have, I can move it like this, I can move it like this, and I can also rotate it. But the rotation doesn't come from the wrist. Okay? So if you hold it here and move it, there are only 2 motions possible. Okay? So you have seen this kind of a joint. It's called a Hooke's joint or a universal joint in mechanical engineering. Okay? It has basically 2 motions. I cannot rotate my wrist with respect to my lower arm along an axis through this, okay, along a longitudinal axis. That is enabled actually by, if you hold the elbow, you can rotate that. And that comes from two boards sliding with respect to each other, okay, on each other. And this is enabled by that, okay. So this particular rotation is enabled by the way the bones are connected here and how it's connected here. So if you assume that that is part of this joint, this can be a spherical joint, okay. So how many degrees of freedom altogether? So degree of freedom, so let me come to that. Degree of freedom is a very crucial concept in robotics or in mechanisms. In very simple terms, I have this arm. If I ask the question, how many actuators, minimum number of actuators are required in order to move my arm in a specific deliberate way? The answer is degrees of freedom, but you have to slightly modify this question, then it becomes degrees of freedom. Okay? So broadly this is what it is. So it turns out that our arm up to this fist, including the fist, if I don't consider the fingers, has 7 degrees of freedom. 3 here, 1 here, and 3 here. Okay? And the fingers by themselves have 20 degrees of freedom. So altogether our arm has 27 degrees of freedom. A typical robot has 6 degrees of freedom. A typical capable robot has 6 degrees of freedom. So you can imagine that our arm is significantly more capable as a mechanism compared to a typical manipulator. Okay? So now we are going to see the first 3 joints of a manipulator and separate it out from the last 3 joints, because in a serial chain manipulator, what happens is that the first 3 joints are there in order to make the wrist move in 3D space, in a region. It traces out a region, and the first 3 joints does that, not necessarily in all cases the first 3, but typically. And so there are 2 parts to a robot, a serial chain robot. One is called the regional mechanism, which gives the movement, ability to move in a region. The other is called the orientational mechanism, which basically is used to orient the end effector or the fist in various ways. So it is split into 2. We are first going to see regional mechanisms, basically the first 3 joints or the first 4 links. So what you see here is what is the most common type of regional mechanism. There is the base, there is the base, this is the base. This moves with respect to the base in this direction. And then there are these things here. So this moves up and down with respect to the second link, which is this. And this moves to and fro with respect to that, in this direction. All these are implemented through what are called slider joints or prismatic joints. So this can only translate in this direction, this can only translate with respect to this in this direction, and this can only translate in this direction with respect to this. But because they are connected in series, if you look at a point like this, this can make translatory motions which are 3-dimensional. Okay? So this particular point typically can reach within a rectangular workspace. You can attach a wrist here and a hand here, then it becomes a full robot. Okay? So this is and this is a typical example of this. So this is what is called a gantry configuration. You have seen gantry cranes. This is a typical configuration of gantry cranes. Now a little more complex, still not all that complex. You introduce one revolute joint at the base here. Okay? So that allows this to rotate. Otherwise there are just 2 prismatic pairs, one which allows this to move up and down, and this can slide like this. Now if you ask the question, what kind of region can this particular point reach? Okay? Because these 2 joints are there, this can, if you lock this can reach within a plane, a rectangular planar region, and this rotates the rectangular planar region about this axis. Because of that, it forms an annular cylindrical region. Okay, so this is called a cylindrical robot because of that. Now the first robot which you saw working has this particular configuration. where the base can move up and down. Okay. So on the base, the first link can move up and down. There is a revolute joint here, so this link can rotate, and there is another revolute joint, and so this link can rotate with respect to this. So two revolute joints and one prismatic joint. And again, if you ask a question, what is the region that this end can reach? That also turns out to be annulus of a cylinder, because if you log the up and down motion and look at what is the region which this can reach, it turns out to be the annulus of a circle or a disc with a full disc perhaps, or a disc with a hollow region inside, and this actually moves it up and down, so it becomes a full cylinder. So both these are called cylindrical configuration, and this particular configuration is called SCARA, which stands for Selectively Compliant Articulated Robotic Arm. This is one of the configurations initially developed for assembly operations, because this is selectively rigid in certain directions and not that rigid in certain other directions, which is something very important for assembly. Okay? So this is the Motorman robot that you saw. There are two more configurations here. This one has a base rotation like this, and a further rotation about a horizontal axis like this, and then there is a prismatic joint like this, telescopic joint like this. So this can move in and out, and this particular point can reach anywhere within an annulus of a sphere. Okay, so because of that, this is called a spherical configuration. There is another spherical configuration, and this is pretty similar to our arm. Okay, there is a shoulder joint where there is this rotation as well as this rotation. Our shoulder has one more. This is two here, and then there is this thing like our upper arm, and this like our lower arm, and there is a further revolute joint here. So three revolute joints. Okay, this is the first time out of all the configurations, this is the one which has only revolute joints, and this is called, also has a spherical region which can be worked out, that it is spherical, and this is called articulated because it has only revolute joints. Okay, so these are typical configurations of regional mechanisms of serial chain robots. And at the end of this, you have the orientational mechanism, and this is one of the most best known kind of orientational mechanism. This is not the best known. There is another which is called a Bendixson wrist, which is very, very interesting mechanism made with bevel gears. This is something a little different, but this will serve the purpose. This is the lower arm. Okay, there is a revolute joint like this about which this can rotate, and then there is another revolute joint which is perpendicular to this, about which this can rotate like this, and finally there is another revolute joint which enables this to rotate like this about this axis like this. So there are three revolute joints, so somewhat similar to our wrist. But this does have a problem. If we put it in a robot, then the calculations which we are going to see in the afternoon becomes really difficult. So, but this is nevertheless a typical wrist. So it's shown sitting here, and I think what is shown here is the Bendixson wrist, which is different. So this is a typical wrist. Okay? So I said this is a concurrent wrist. This is not a concurrent wrist. I was wrong in saying that. This is a concurrent wrist. Concurrent means the last three axes of the revolute joints intersect each other at a fixed point. Okay. Okay. Now there is another mechanism in the robot which is very important, which is the last part, the gripper. Okay. You see three very simple grippers here. This gripper can close like this, whereas this can translate like this, and this also translates using a very simple prismatic joint. This translates using a set of a different kind of a mechanism. But the most capable one is this. Okay, this is almost like the human hand, and this is several degrees of freedom. Most of them independently controlled. Our hand, although we can independently control the various joints here, only a very capable person can do it very well. Most of us actually do not develop the independent motions very well. Okay? We don't need to in the normal operation, so we don't develop it very well, but we can make it control it independently. And this is capable of being controlled independently. Okay, so now let us come to the parallel manipulators. What you see here is not a mechanism with links in series. This is exactly what you saw doing that pick and place of balls very fast. Okay, it is called the quattro, and there are 4 arms here which move independently in order to make this move. Okay. So if you simply interconnect mechanisms like this, links like this, will it have motion, particularly the kind of motion we want to give it, is a very important question when you try to design something. And that is actually the question which is answered by the concept of degrees of freedom. I just want to introduce that here. So the real question is this: how many independent inputs? So earlier I said how many actuators. Actuators, the input is force, but here we have to go away from force and consider motion as input. So we are looking at kinematic inputs. Okay, how many independent kinematic inputs are required to move a mechanism in a determinable way? Okay, in a well-defined way, so that nothing remains loose to move by itself without our control. So everything moves in a well-determined way. The answer to this is degrees of freedom. Okay, this can be defined more mathematically, but this is good enough. And it turns out that we can derive it very easily. If a mechanism has n number of links and we keep one fixed, then, and if it has several joints, each joint could have different degrees of freedom. So Ji is the number of joints with I degrees of freedom. So revolute joint has 1 degree of freedom, prismatic has 1, spherical has 3, cylindrical has 2. So there are different types of joints with different degrees of freedom. So if you simply count the number of links and the number of joints with different degrees of freedom, there is a formula which gives the degrees of freedom. Okay, and this is something you can derive very easily. I don't want to get into the derivation, but this we can apply and find the degrees of freedom. In almost all cases, in some cases this is violated. So let us see an example, but let me first describe this particular parallel manipulator. So this is a very simple sketch, schematic sketch of a very capable configuration of a fully parallel manipulator. The configuration is very, very simple. There is a base which is fixed and there is an end link, which is what we want to move. Now look at one arm which is connected between the base and the end link. You have this particular link which has a cylinder, and then there is a piston here and that is connected to this link. The cylinder, let's assume for the moment, is connected to the base through a spherical pair. Okay, and the piston is connected to the end link through a spherical pair. There are 6 such arms, identical, positioned at various different points. Now if you work out the degrees of freedom of this particular mechanism, there are 14 links and there are 6 joints with 1 degree of freedom. Those are the prismatic pairs here. Okay, and there are 12 joints with 3 degrees of freedom. So 3 degrees of freedom here, 6 like that on the base, 3 degrees of freedom here, and 6 like that on the end effector. And the degrees of freedom turns out to be 12. Okay, whereas this particular end effector needs to have only 6 degrees of freedom. It can have only 6 degrees of freedom. You cannot have really more than that. Whereas this total mechanism has 12 degrees of freedom. What happens is that the piston cylinder assembly can rotate about an axis through these 2 spherical joints, and that is an unwanted motion which is not really required, and that is not going to give any motion to the end effector. So it is not really required, a rotation, so it can be arrested, and what is done really here is to arrest that. The dark circle that you see represents a Hooke's joint, a universal joint. Okay, it's not a spherical joint. This has only 2 degrees of freedom as against 3 degrees of freedom of a spherical joint. So if you put this here, this rotation is arrested and you end up having 6 degrees of freedom. This is what you want. The danger with this rotation is that you may have some wires actually along this. If we keep rotating too many times, the wires snap. You don't want unnecessary things like that. So you would like to arrest that. And so this is the better design. So this mechanism is the famous, the generalized version of the Guff-Stewart platform. Okay, it was first built for a very fascinating reason. They wanted to move a stage where a play was taking place. Okay? A large stage like this had to be moved in a particular play, and this was used. The most common use of this is for aircraft simulation. The cabin is moved by a mechanism like this. Okay? The biggest advantage of this as against a serial chain is that this is able to support a lot more force than a serial chain can. A serial chain sort of cantilevers out, whereas there are, in this particular case, 6 parallel flows for force. Okay, it's much more rigid and much more capable of applying force than serial chains. And this is a version of this which also has 6 degrees of freedom only, because there is a spherical joint here and there is a spherical joint here, and there is a Hooke's joint here. Okay, almost the same. You can work out the fact that this also has 6 degrees of freedom. There are other very interesting parallel mechanisms. This is called a delta manipulator. It is a very funny configuration. I wouldn't go into the details of this now, but if you count things, it turns out to have minus 9 degrees of freedom, which means that it cannot move, but it has actually 3 degrees of freedom. The 3 degrees of freedom turns out to be pure translation of the end effector. It cannot rotate at all. Okay? It can only translate. This is again something you can work out, the fact that it has actually 3 degrees of freedom. And again, if you put this particular gripper here, and if you want to rotate it about this longitudinal axis, this cannot do it. Instead of that, you can put a motor here and supply a transmission to rotate that, and that is what is done here. And this is called the flex picker with 4 degrees of freedom. Okay? So, and the most capable guy in this, and one of the most capable guys in this, is the Quattro, which we saw picking balls and placing it. We couldn't almost see it, it was so fast. Has 4 arms like this, and it is 5 degrees of freedom. It can give a translation as well as 2 rotations. Okay? So these are the typical robot manipulators which are common. Let me now come to wheel robots. These 2 are very common configurations. Almost all of you have seen this. Both are tricycles. This has 2 degrees of freedom. Both have 2 degrees of freedom. This is both driven as well as steered by this wheel. So these 2 wheels are passive. Okay. So this has 2 degrees of freedom. Whereas in this particular case, these are the active wheels. There are 2 independent motors here. This is a passive spherical kind of a wheel. It can be a caster wheel or it can be a sphere. And these can be independently driven. Now one problem with this is that this cannot move in any fashion that you want it to move. This can only move by rotating about a point which is on this axis. Okay? And this also instantaneously has to rotate about a point on this axis. Unless you allow sliding. If you don't allow sliding, it can only do that. Whereas the next one which I wanted to show is capable of moving in any way you want it to move. This is one of the most fascinating designs that you will see of wheeled vehicles. It is enabled to move in whatever way it wants to by these special wheels which are called Swedish wheels. Okay? A Swedish wheel is a wheel like this which is basically rotated about this axis to make it move forward. And these additional wheels here which enables it to move passively in other directions. Okay? So if you look at it from above, these 4 wheels are put on a vehicle here. This cannot steer. you cannot steer the wheel or rotate the wheel about a vertical axis. But if you look at this can passively move in this direction, actively move in this direction. Okay? So all these wheels are like that. Now if you want to rotate it about any point, a general motion of a rigid body in the plane instantaneously is rotation about an instant center. Okay? Or translation. So if you wanted to rotate about any point, whatever be the point, what is required is that with respect to that particular point, the velocities given at these 4 contact points with the ground should be consistent. Okay? And those should be